So we're going to continue with section 3-4, and the first thing we're going to talk about are complex conjugates. So if you have the complex number a plus bi, then its conjugate is a minus bi. Basically, you just change the sign on the imaginary part. So if you multiply a complex number by its conjugate, here's what ends up happening. So I'm going to go ahead and use FOIL. So I'm going to do the first, or get a squared. And then the outer, I get minus abi. And then the inner, I get plus abi. And then the last, I end up getting minus b squared I. I can cancel out these terms right here. And remember that I squared is -1. So I'm going to replace I squared with -1. So I end up getting a squared, and then minus a minus turns plus b squared. So this right here, there's no imaginary number with it, so this is a real number. So one of the biggest things, or the most powerful things for a number and its conjugate is when you multiply them, you'll always get a real number. So a numerical example would be to take 2 plus 3i and multiply it by its conjugate. So all you need to do is change the sign on the imaginary part. So it would be 2 minus 3i. Oops. There we go. And then we're going to multiply that by 2 plus 3i. So I'm going to go ahead and FOIL this out. So first, I end up getting 4. Then the outer, and I end up getting plus 6i. The inner is minus 6i. And then the last is minus 9i squared. So the 6i's end up canceling out. The I squared is going to be replaced with a -1. So basically I get 4 plus 9, or 13. That formula right here, if I know what a and b are, I can just square it. So a is 2, and b is 3. I could have just done 2 squared plus 3 squared to get the result really quickly. And that will always work when you multiply a number by its conjugate. So the next concept is dividing complex numbers. And what you're going to do is you're going to multiply the numerator and denominator by the conjugate of the denominator. So here's an example. So I have 5 plus 6i over 1 minus 3i. And one thing for you to note is that you can never have an imaginary number in a denominator. It's not considered to be simplified or proper. So we want to get rid of it. And if you remember, the only way to get rid of a complex number is to multiply it by its conjugate, because you get a real number. So in the denominator, I'm going to multiply by 1 plus 3i. Now remember, whatever you do to the bottom, you have to do to the top. This is like multiplying by a 1 right here. So I'm going to go ahead and FOIL this thing out, top and bottom. So I'm going to put my parentheses here, and I'll do the top first. So starting here, I'll end up getting 5. Here I get plus 15i. Here I'll get plus 6i. And the last, I end up getting plus 18i squared. Alright, the denominator, I can use the little shortcut if I want. It's a squared plus b squared. That's a and that's b. So I basically get 1 squared plus -3 squared, and I end up getting, what is that, 10? The numerator, I can go ahead and simplify. I'm going to go ahead and replace I squared with -1. So I end up getting 5 minus 18. So I end up getting -13, and then I can go ahead and add these two right here to get plus 21i. So you can leave the whole answer under 10, or sometimes the book actually separates the real part and the imaginary part. So they'll write it as -13 plus 21i over 10, just so you can identify the real part and the imaginary part. This would be the real, and then the 21/10 would be the imaginary part. So we're going to go ahead and square root negative numbers this time, and you're going to simplify the square root as if it was positive, and then you're going to add an I to the answer. That's the only difference, because you can't take a square root of a negative number. You start going into the imaginary numbers. So let's go ahead and start with this example. Square root of negative 36. Well, what you can do if you want is you can go ahead and break it up into the square root of 1 times the square root of 36. And you can say, oh yeah, the square root of negative 1 is I, and the square root of 36 is 6. So this is the same thing as 6I. Or you can use the hint that I just told you. So you just simplify the root. What's the square root of 36? It's 6 because it's negative. Tack on the I to it. For this example, the square root of negative 5, you can't simplify root 5, so all you would say is this is I root 5. In this example, you're asked to simplify this expression, and usually what I like to do is simplify my roots before I actually FOIL. So I'm going to go ahead and simplify the square root of 63. Its factors are 9 and 7, and I can root 9. So this is the same thing as 3 root 7 minus, and then this is, because it's negative, is imaginary, so I'm going to get minus I root 7. And then I'll get 7 plus, and then the square root of negative 9. Well, square root of 9 is 3, but because it's negative, it's imaginary. So I'm actually FOILing out that. So I'm going to go ahead and distribute this out. So when I end up doing that, I'd multiply the real parts. So 3 times 7 is a 21. And then I have the root 7. And then I'm going to distribute this here. So the 3 times the 3 is a 9. And then there's an I. And then I have the root 7. And then distribute that out. I get minus 7I root 7. And then last but not least, I have a negative 3I squared root 7. So replacing my I squared with a negative 1, this basically right here comes out to be plus 3 root 7. So when I combine like terms, my real parts I combine, so they have root 7 in common, so 21 plus 3 is going to give me 24 root 7. And then when I combine my imaginary parts, these two guys right here, I get plus 2I root 7. So that would be this expression completely simplified. The last concept is quadratic equations with complex solutions. Pretty much if the quadratic does have complex or imaginary solutions, it's not going to be factorable. So whenever something is not factorable, you're going to have to use the quadratic formula. So here's an example. So you're asked to solve this quadratic, and most people generally start by trying to factor it, find two numbers that multiply to 5, add to 4, and you try 5 and negative 1, that adds to 4, but it doesn't multiply to 5. So it's not factorable. I told you anything with an imaginary solution isn't going to be factorable, so you got to go right to the quadratic formula. So you have A is 1, B is 4, and C is 5. So I get opposite B plus or minus the square root. B squared is going to give me 16 minus 4A, and C is 5, all over twice A. So when I go ahead and simplify, I end up getting inside the square root 16 minus 20. So that would come out to be negative 4 plus or minus the square root of negative 4 all over 2. And the square root of negative 4 simplifies into 2i. So I get negative 4 plus or minus 2i over 2. And remember, when we simplify, that denominator has to simplify with both in order to reduce. So I end up getting negative 2. Let's try that. Negative 2 plus or minus I. So you have imaginary or complex solutions. What does that mean in terms of the graph? Well, if I were to sketch this, I would get 1, 2, 3, 4, 5. If I plug in 0 everywhere there's an x, I get 5. Plug in some more numbers, my quadratic would end up looking like this. And because I have imaginary, remember these are zeros, what you're finding when your equation is equal to 0. Zeros are x-intercepts. Because they are imaginary, What that means is that this parabola, this quadratic, never crosses the x-axis, thus the imaginary solutions. In section 3-5, which is about complex zeros, we're going to be first starting off factoring a polynomial completely from its zeros. So there's two steps when doing this. Step 1 is to find the zeros. So when you do this, you'll set the polynomial equal to 0, factor if you can, and then go ahead and solve for them. Step 2 is you are going to write the factors from the zeros. So basically, once you get the zeros, you can go ahead and write the polynomial in factored form. Let's go ahead and start off with an example. So we're going to factor x cubed plus x squared plus 81x plus 81 completely. And so we're going to follow the steps. Step 1 is you're going to be finding the zeros. So we're going to go ahead and set this thing equal to 0, and then we're going to factor by grouping. So when we factor by grouping, we're going to group the first two together and the second two together. We can take out an x squared in the first group and we're left with x plus 1. And we can take out a positive 81 in the second group and we're also left with an x plus 1. So when I go ahead and factor this, I have the x plus 1 that's in common, and then what's left over is an x squared plus 81. And I'm going to go ahead and find the zeros, so I'm going to set each factor equal to 0. So x would be negative 1 for this factor. When I set this equal to 0, I'll go ahead and move over here. I would subtract 81 to both sides, so I get x squared equals negative 81. And when I square root, I'm not going to forget the plus or minus. So I'm going to get x equals plus or minus, and since it's a square root of a negative, I'm going to have 9i. It's going to be imaginary. So I have all of my zeros. Notice there's 3 zeros. The degree is 3, and it follows the fundamental theorem of algebra. So step 1 was to find the zeros. Step 2, we're going to write the factors from zeros. Remember, our goal is to factor this polynomial completely. So in order to do that, we're going to go ahead and write the zeros in factored form. So this came from the factor x plus 1. You can see that right here. And then I'm going to use these right here to write the other factors. So I will have x minus a 9i and x plus a 9i, and this will be that polynomial factored completely. You basically just get all the zeros and then write the factors from that. So in this example, we have a 4th degree polynomial, and we're asked to factor it completely. So remember, step 1 is to find the zeros. Well, I have 5 terms. There's no factoring technique that we've covered to do this, so this is where we're going to have to go to the graph to get us started. So I went ahead and used the graphing calculator, and I graphed our polynomial to get us started to find a possible 0. So I'm going to go ahead and use this one right here. It looks like x equals 1 is a 0, so I'm going to go ahead and test it to make sure. So using polynomial division, taking my coefficients here, 1, negative 3, 7, 21, and negative 26, I'm going to see if this actually does have a remainder of 0. So I'm going to put a little question mark right here. So bringing down the 1, multiplying, and going through the process of adding, I end up seeing that I am going to actually get a remainder of 0. So instead of question mark, I'm going to put check, so it does check out. So when I go ahead and start factoring, the factor that came from 1 is x minus 1. And then I'm going to have an x cubed minus a 2x squared plus a 5x plus a 26 to now factor. So now when I try factoring this by grouping, I can take out an x squared in the first group, but I can't take anything out in the second group besides a 1, and so I'm not going to get a common factor. So this is where we're going to have to go back to the graph. So we're going to go ahead and try the other 0. So it looks like that's negative 2. We're going to go ahead and plug that in. So we'll put negative 2 in. And remember, our goal is to factor this one now. So I'm going to copy down the coefficients, 1, negative 2, 5, and 26. And then go ahead and do the process of synthetic division. So I end up getting negative 4, 8, 13, and then here I get negative 26, which is a 0, so check. So now, when I go ahead and write my factors, I still have the x minus 1 from before. I have the x plus 2 from this guy right here. And then what's left over is this down here. I have an x squared minus a 4x plus a 13. And remember, this whole thing is equal to 0. So when finding my zeros, I get x equals 1 and negative 2 from these two factors. So there's 2 of my zeros. This doesn't factor, so I'm going to have to use the quadratic formula. So I get opposite b, which is 4, plus or minus the square root, and then b squared would be 16, minus 4 times 1 times 13, all over twice a, or twice 1. So when I go ahead and simplify this, I'm going to go right up here to the top. I end up getting x is equal to 4 plus or minus the square root. This guy right in here ends up simplifying to negative 36. So I end up getting 4 plus or minus the square root of negative 36 all over 2. And I end up getting 4 plus or minus, this is going to be 6i all over 2. So it looks like my zeros are 2 plus or minus 3i. So I have my 2 zeros from here and my 2 zeros from there to get my total of 4 zeros. So I've cleared some space and I have all my zeros right up here, the 4 zeros we just found. And now our goal is to write them in factors, or factor it. So I'm going to start off with the first 2 zeros. So if 1 is a 0, then x minus 1 is a factor. If negative 2 is a 0, x plus 2 is a factor. And then all you're going to do is do x minus your 2 other factors. So one of the factors is 2 plus 3i. And then the other factor is x minus and then 2 minus 3i. So you basically are just doing x minus for each of these and then putting your 2 other zeros. So then when I simplify this, I have the x minus 1 and the x plus 2. And then I can go ahead and just distribute this negative through to write my complete factor. So I get x minus 2 minus 3i, and then here I will get x minus 2 plus 3i, and this would be my polynomial completely factored. So the process is the same for all of these. You're going to find the zeros, get your answers, and then write the factors from those zeros and simplify. So the last part of this section focuses on writing polynomial equations from its zeros, and we're going to talk about the conjugate zero theorem. And it states if a plus bi is a 0, then a minus bi is also a 0. So basically, if you have an imaginary number, its conjugate automatically is a solution as well, so they always come in pairs. So in this example, we're going to find a polynomial that's degree 3 and has zeros negative 3 and 1 plus I. Now if you remember, the degree and the number of zeros have to be the same. So it says it's degree 3, and I only gave you 2 of the zeros. Well, because of the conjugate zero theorem, we know that if 1 plus I is a 0, we also know that 1 minus I is a 0 because they come in pairs. Thus I have my 3 zeros to match my degree. So now we're going to do what we did before. We're going to go ahead and write the factors from our zeros. So we're going to call our polynomial p of x. And a factor, if you have negative 3 as a 0, it'll be x plus 3. And then we're going to do x minus the first complex 0, so 1 plus I. And then we have x minus, and then the second one, 1 minus I. And then now we just have to go ahead and simplify this. So we're going to leave this, simplify this out right here. So I'm going to go ahead and distribute the negative through for each of these. So we have x minus 1 minus I and x minus 1 plus I. And now it's just a matter of simplifying. So if you want the exact polynomial and you're asked to actually state it and not leave it in factored form, you're going to have to do FOIL and FOIL like mad. So you're going to distribute that x to each of those. We're going to leave the x plus 3. We're not going to do anything with that yet. So the first FOIL will give you x squared minus an x and then plus an xi. Then I'm going to go ahead and do FOIL on the next piece. So I'm going to take the -1 and distribute it to the 3. So I get minus x plus 1 minus I, and then I'm going to do the last piece. So this to all 3 of those. So I get minus xi, and then I'll get plus I, and then I will get minus I squared. Okay, so now let's combine like terms, simplify. So I believe that xi's are going to end up canceling. So this xi with that one. I have the i's also canceling, so I'm going to cancel this out with that. Remember, I squared is -1, so I have minus a minus, so that actually ends up being +1 right here. So now I'm going to have the x plus 3 times the x squared, and then it looks like I have 2 x's, so minus a 2x, and then it looks like I have this +1 and this +1 for a +2. So to continue even further, you'd go ahead and FOIL that out. And after you FOIL it out, I believe your final answer will be this after you combine like terms and such. So that's it. I will see you guys tomorrow. Have a good evening.